Hello everyone. So today we are going to talk about an important concept in TOC, theory of computation. So that is undecidability. So first let me tell you what is meant by undecidability. So a decision problem is undecidable if there does not exist any Turing machine so that holds on every input and correctly accepts or rejects based on the each input. So that means for some inputs, the machine would either be incorrect or never halt in a machine and therefore cannot be will be considered a deciding algorithm. So that is called undecidability. So in this undecidability, under this topic, today we are going to discuss the subtopics recursive and recursively enumerable languages, and next a language that is not recursively enumerable, and an undecidable problem that is regular enumerable language, and undecidable problems about Turing machine, and also we are discuss about the polynomial time reductions, and the last one is traceable and intraceable problems. Also we are going to discuss. So first we'll discuss about recursive languages. First, recursive language, also known as decidable languages. So a language that is denoted by L, capital L, is said to be recursive. So if there exists a Turing machine that can always decide whether a string that is belongs to L or not. So first let me tell you what is meant by this recursive language. So if the input string W is in L, that means W input string is in the language L, the machine accepts it. If the input string W is not in L, that means the input string is not in the language, the machine rejects it. So that's why here we have the two states, accept and reject state. So the key point here is that the Turing machine never runs forever. So it always halts after a finite amount of time. So that can be providing a definite answer. So let me give you an example now. So consider the language of all strings with balanced parentheses now. Okay, say a Turing machine can examine any input string of parentheses. So it will check whether it is balanced and halt with an accept or reject state. So recursive languages are those for which membership can be decided algorithmically in some finite amount of time. So that is called the recursive language. So this is all about the recursive language. So next we will discuss recursively enumerable languages. Okay, next let's move on to the next second type. Recursively enumerable language is also known as semi-decidable language. So already I told you that recursive language is also called as a decidable language. So this recursively enumerable language is also called as the semi-decidable languages. So here a language which is denoted as capital L also. So it's recursively enumerable. If there exists a Turing machine, so that can recognize strings belong to this language L. So now let me tell you how it works. So for example, if the input string W, okay, is in the language, particular language L, then the machine accepts it. And also if the input string W is not in L, that is not belongs to L, the machine may either reject it or loop for forever. So that is called the recursively enumerable language. Now I will tell you some key points of the recursively enumerable language. So that the Turing machine is guaranteed to halt only on strings. So that are members of the language. So for example, So let us consider the language of all valid mathematical theorems. So now a Turing machine can systematically enumerate proof and alt if the input is the theorem here. Okay. So but if the input is not in a theorem, the machine may run indefinitely without giving any answer to us. So recursively enumerable languages are those where membership can be recognized, but non-membership may be undecidable here. So this is all about the recursively enumerable language. So now let's explore the relationship between recursive and recursive enumerable languages. So first, every recursive language is also recursively enumerable, right? Now I will tell you the reason. So why? Because if a Turing machine halts on all inputs, so it obviously halts on members of the language as well. So however, not every recursively enumerable language is recursive. Some recursively enumerable languages have inputs not in the language where the Turing machine may loop forever. So it can making them undecidable. Okay, now I will tell you in simpler terms. We can represent it like this. This recursive and subset of recursively enumerable. So here's here differentiate between the recursive and recursively enumerable. So it is a residable one. The Turing machine halts for all inputs and it says yes or no. That is our output. In recursively enumerable, it is also a semi-decidable. The Turing machine halts only for yes cases, but may loop forever for no cases. So here we have the two cases, yes and no case. In yes cases, the Turing machine halts only for yes case, but it may loop forever for no cases. So now we should understanding this hierarchy help us to see which problems are fully decidable and which can only be recognized but not always decided. So this is the relationship between the recursive and the recursively enumerable language. Now let's discuss about recursively enumerable language in more detail on how they relate to undecidable problems. Okay, let me tell you now. First, a language is recursively enumerable or recursively enumerable if there exists a Turing machine M. Okay, let us consider if there exists in Turing machine M that accepts every string in the language, particular language, and does not accept string that there are not in the language, right? So now to prove a language is undecidable. So first we have to consider the language consisting of pairs M, W here. M represents the machine and W represents our string such that M is a Turing machine that is encoded in the binary with the input alphabet 0 and 1. So already we know that W is an input string of zeros and ones. So this M accepts input W. So it's important that the input W is represented in the well-formed binary encoding. So by this understanding, we often follow these steps. First, we should enumerate all binary strings. So let us consider codes for Turing machines and we have to construct a diagonalization language to show that some languages cannot be decided by any Turing machine. So this approach will demonstrate that while a language may be recognizable, so it may still be undecidable, right? So meaning there is no Turing machine that holds on all inputs for that language. So this is all about the language is not recursively enumerable. So here's an important theorem in the TOC. So what is the theorem is here? If a language L is recursive, then its complement, that means the complement of L dash is also recursive. So we have to prove that this theorem is true. Okay, let's see why this is true. So we can prove this by constructing a halting Turing machine. So that accepts L. Suppose here we have a Turing machine M. Okay, um, that accepts the language L. So this Turing machine M always halts on every input. So now we construct a new Turing machine M dash. Okay, so let us assume that we can construct a new Turing machine M dash, so that behaves like M, but with a twist here. So this M dash accepts an input if and only if M rejects it. So in other words, M dash decides the complement of L, which is L dash. So here, since M halts on all inputs, so as well, the M dash also halts on all inputs. Therefore, if L is recursive, its complement L dash is also a recursive. So this theorem highlights that recursive languages are closed under complementation. So here we can see that the Turing machine M, and it receives the input string W. So here we have the two state. This Turing machine may accept the input, will produce the output as in accept state. Otherwise it will reject in the reject state. Okay. Then when it comes to the complement of L, that means the result will be the opposite of this Turing machine. This reject will be converted into the accept, and this accept will be converted into the reject. So in this tabular column, uh, we have desired have M Turing machine, and at the right hand side M dash Turing machine. So this M Turing machine which accepts the input, then the M dash Turing machine will reject the input. Suppose if the M Turing machine will reject the input string, this M dash Turing machine will accept the input string. So that is what it represented with M and M dash. So next we'll move on to the next theorem. So the next theorem is recursively enumerable language. The theorem is the union of two recursively enumerable languages also recursively enumerable. So here we can say that if L is that is equal to L of M1, that is the Turing machine M1, that is union of L of M2, where M1 and M2 here are represent the Turing machine and also recognizing the languages L1 and L2. Then L is recursively enumerable here. So now let's prove that the L1 and L2 be languages or recognized by Turing machines M1 and M2 respectively here. So we can construct a new Turing machine M that on input W. Okay, so that can simulate the M1 and M2 in parallel. So if either M1 or M2 accepts the same input string W, then M accepts W. Since we can design M to enumerate all accepting paths, the new machine recognize the union L1 union L2. So it shows that recursively enumerable languages are closed under the union. So that's why here under we can see that L1 accepted by the Turing machine M1, L2 also accepted by the Turing machine M2. So that can be represented in L, that is equal to L1 union L2, that is also accepted by the machine M1 union M2. So thus here we can see that in the tabular column if L1 and L2 are recursively enumerable, so then the union L1 union L2 is also recursively enumerable. So it shows that the regular languages are closed under the union. So it means that we can always construct a Turing machine to recognize the union of two recursively enumerable languages here. So the next theorem is the intersection of two recursively enumerable languages is also recursively enumerable languages. So that is represented if L is equal to L of M1, that is intersection symbol, and we have the L of M2. So here already we know that M1 and M2 are the Turing machines. So that can recognize the language L1 and L2. So then L is recursively enumerable here. So now let us prove that this L1 and L2 be languages recognized by Turing machine, M1 and M2 respectively. So what we have to do is now, so first we can construct a new Turing machine M that on input W. So it can simulate M1 and M2. So now this M accepts W if only both M1 and M2 accepts W. So we can ensure that M recognizes exactly the strings in L1 intersection L2. So for that we can making the intersection recursively enumerable here. So sorry languages are closed under intersection. So just as they are under the union also. So here L1 is accepted by the Turing machine M1. The L2 is also accepted by the Turing machine M2. So both are intersected with each other. So the output is, we can see on this table, and clearly the constructed Turing machine M recognize the language L1 intersection L2. If M1 and M2 holds on all inputs here, then M also holds on all the inputs. So therefore, if L1 and L2 are recursively enumerable, then the intersection of L1 and L2 is also recursively enumerable. So the recursive languages are closed under intersection. So now let us discuss an important property of recursive languages. The theorem is the union of two recursive languages is recursive. Similarly, the intersection of two recursive languages is also a recursive. So now let us prove that L1 and L2 be recursive languages. Okay. So to prove that L1 union of L2 is recursive, so we need to construct what we have to do. First, we have to construct the Turing machine M. So that can recognize this union. So now let M1 and M2 be the Turing machine here, and that can accept the languages L1 and L2 respectively. So we can construct M as follows on input W. So this M first simulates M1. If M1 accepts the input string W, then M accepts the W. Otherwise, M simulates M2, and also it accepts if M2 accepts W. Since M1 and M2 are always halt because L1 and L2 are recursive, right? So M also always halts. So thus the union of two recursive languages is itself recursive. So in this diagram itself we can understand easily. So next, since M1 and M2, the components of M are recursive and have algorithms that always halt. M is also guaranteed to halt on every input. Therefore, M correctly recognizes the language L1 union of L2. So it can prove that the union of two recursive languages is recursive. So we have the next theorem here. If the language L and its complement L dash are both recursively enumerable, then L is also recursive. So we have to prove that. So now let us consider the Turing machine M1 and M2. that accepts the language L and L dash respectively here. So first we have to construct a new Turing machine M. So that simulates M1 and M2 simultaneously on the same input, right? Since every input must belong either to L or L dash. One of the machines will eventually accept. Therefore, M halts on all inputs. So that can be deciding membership in L. So this shows that if a language and its complement are both recursively enumerable, then the language is recursive. So we can prove this theorem. So here the constructed Turing machine M works as follows. So M accepts if M1 accepts. M rejects if M2 also accepts. Since any input W which belongs to either L or L dash, we know that exactly one of M1 or M2 will accept. So thus M will always provide a definite answer either yes or no. So therefore M as an algorithm here, so that decides L, and the machine never loops indefinitely. So this proves that theorem. So if a language and its complement are both recursively enumerable, then the language is recursive. So let us discuss two fundamental problems in computability theory here. So the acceptance problem and the halting problem. So first, let me tell you the acceptance problem, that is ATM, that is represented ATM here. Okay. So that is ATM, that is acceptance problem, that is equal to M comma W, such that MTM, that is MTM, that is Turing machine, accepts input W. So here we can build a universal Turing machine. So that can simulates M on W. So here we can say that if M accepts W, that means the input string, then the UTM, that means universal Turing machines, can halt and accepts the same input string. If M does not accept the input string W, so we can say that then the universal Turing machine may run forever. Hence, this ATM is semi-decidable or recursively enumerable. Now, I will tell you why it is undecidable. So there is no general algorithm that can decide for all pairs, that is M comma W. Whether M accepts W, this is proven by a reduction from the halting problem. So now we'll move on to the next problem is halting problem. Halt TM. So here the same halt Tm, that is equal to M comma W, such that Tm, that is Turing machine, halts on the same input W, input string. So here we can simulate M on W if it halts or accepts. So here we can say that not recursive, there is no Turing machine that can decide halting or all inputs, which can be proven by contradiction. So these problems can be illustrate the limits of computation, showing that some languages are recognizable but not decidable here. Next, we'll discuss about the non-trivial properties of Turing machines. Any non-trivial property of a Turing machine that depends only on the language it accepts must be undecidable here. So there are also undecidable problems that do not directly involve in the Turing machines or any other languages. So for example, let us consider a Turing machine that accepts the empty language. During the reduction process, here we can define two special languages. One is empty language and another one is non-empty language. So in empty language, here we can consist of binary strings such that L of mi that is equal to 5. So the meaning of the Turing machine accepts the no strings. So that is empty language. In non-empty language, that is LNE, so that will discuss in the next slide. That is in the next slide. Non-empty language. So consider a Turing machine MI so that does not accept any input. Then MI belongs to the empty language. LE that is equal to M such that L of M that is equal to 5. So this consists of all encoded Turing machines whose language is empty. Now let us consider the non-empty language, that is LNE, where MI accepts at least one input. So that here LNE that is equal to M such that L of M that is not equal to 5. So which represents of all codes of Turing machine that accepts at least one input string. So the both LE and LNE are languages over the alphabet 0, 1 and are complements of each other. So this LNE is recursively enumerable but not recursive. So while we take the LE is not recursively enumerable. So now we can understand the decidability and semi-decidability in Turing machine theory. I hope you all understand what is meant by decidability and semi-decidability in the Turing machine. Next, we are going to discuss about the Rice theorem. So here, any non-trivial property of recursively enumerable language is undecidable. So first, I will tell you about what is meant by trivial property. The property P of RE languages is trivial. So if it is either empty or satisfied by no language or it includes all regular enumerable languages. Otherwise, the property is non-trivial. Let P be a property of RE languages here. Okay. So first we'll take LP as a set of codes for Turing machine MI such that L of MI. So as the property P. So here the theorem is every non-trivial property of recursively enumerable language is undecidable. So that equivalently we can take every non-trivial semantic property of Turing machine is also undecidable. So now let us prove that. Let P be a non-trivial property of an regular language. So first let us assume the empty language phi is not in P, that is property. Since P is non-trivial, there exists some non-empty language L in P. So with ML being a Turing machine accepting L, so to prove undecidability, first we have to reduce LU to LP. Since LU is undecidable here, so the LP must also be undecidable. So first let us consider a pair M comma W. So first what we have to do, we have to construct a new Turing machine M dash such that L of M dash that is equal to 5. If M does not accept W and also L of M dash that is equal to L. Here if M accepts W, so this shows that any non-trivial semantic property of a Turing machine or that is also equivalently of an regular language is undecidable here. So here now let's look at the construction of the Turing machine M dash. So which is used in proving undecidability of non-trivial regular language property. So M dash is a two-tape Turing machine. So here we have the two tape. First tape that is used to simulate M on W. Next we have the second tape that is used to simulate ML on the input X to M dash. So now let me tell you this how this M dash is works. So on input X, so M dash writes the pair M comma W. So onto its first tape. So it then simulates a universal Turing machine U on this pair. If M does not accept W, then M dash does nothing here. So as a result, so here we have M dash never accepts its own input X. So L of M dash that is equal to 5. So this construction is crucial in reductions. So here we have to use to prove that any non-trivial semantic property of a Turing machine is undecidable. So next, this Rice theorem is a powerful tool in computability theory. So any non-trivial property of the language accepted by a Turing machine is undecidable. So here using this Rice theorem, we can prove that the following properties of a Turing machine M are undecidable. So that is represented with L of M that is equal to 5. The language accepted by M is empty. That means L of M is finite and also L of M is regular and also L of M is context free. So in general we can say that all problems about Turing machine so that involve only the languages they accept are undecidable. So any non-trivial question about the behavior of the Turing machine language, whether it is empty, finite, regular or context free. So that cannot be decided by an algorithm. So this Rice theorem highlights the limits of what can be computed when reasoning about Turing machines and their languages. So this is all about the Rice theorems. So here we have the some properties of recursively enumerable is undecidable, emptiness, finiteness, regularity, and last one is the context freedom. So now let's talk about the reduction in computation theory. So first let me tell you what is meant by reduction. So here the reduction is a way of transforming one problem into the another. So suppose here if we have a problem A can be converted into problem B. And so now we can solve the problem B, then we can also solve the problem A. So now let us consider the polynomial time reduction. So that can be written as A less than or equal to P B. So here we have the problem A is polynomial time reducible to the problem B. If there exists a polynomial time computable function f such that, so here the W is a subset of A if and only if f of W is a subset of B. So what is the meaning of this notation? To decide if an input W belongs to the A, so what we have to do? First we have to compute the f of W in polynomial time and then we'll check if f of W which is belongs to the problem B. So this shows that solving A is no harder than solving B. So polynomial time reductions are essential in understanding computational complexity and problem hardness. So next we'll discuss the polynomial time here. So first we restrict to polynomial time because it is considered efficient in complexity theory and also it ensures that the reduction itself does not below up the computation. So now I will tell you the importance of this polynomial time reductions are used to classify problems into classes like P, NP, NP complete and NP hard. So here we have the key idea. If A is say, uh, A is A is in P, sorry, B is in P, then A is also in P. So for proving NP completeness, so reductions are crucial. So to show that the problem X is NP complete. So here we have to reduce a known NP complete problem to X. So the polynomial time reductions are therefore central to understanding problems hardness and the computational efficiency also. So now let's talk about the traceable and untraceable problems here. So first I will tell you what is meant by traceable. So here a problem is traceable if it can be solved in polynomial time. So meaning it can be solved efficiently. And also if the time complexity is bounded by order of n power k for some constant k. So the problem is considered traceable here. So the traceable problems belongs to P, that means the polynomial time class. So now I will tell you the example. Sorting like merge sort with time complexity, that is represented by order of n log n. And also here we have to find out the shortest path using Dijitro's algorithm. So with complexity, order of V part 2 or better. So here we have the minimum spanning tree using Kruskal's or Prim's algorithm with complexity of order of E log V, and also matrix multiplication with the standard order of n power 3 complexity here. So though faster algorithms exist, so the traceable problems are considered efficiently solvable, so making them practical. And let's move on to the intraceable problems. So here a problem is intraceable if no polynomial time algorithm is also known or believed to exist. So these problems require super polynomial time such that 2 power n, comma, n or n exclamatory etc. So classes of intraceable problems, NP hard problems. So which means that at least as hard as every NP problem here. So NP complete problems, the hardest problems in NP. So now I will tell you the examples for this one. Traveling salesman problem, that is mainly used to finding the best solution requires exponential times unless p equal to np. Next we have the Boolean satisfiability SAT, that is NP complete. And also we have the graph coloring problem NP complete, and the 0 bar 1 knapsack problem, that is represents the NP complete. So these intraceable problems are considered computationally hard, so that and solving them efficiently remains one of the biggest challenges in the computer science now. So these are the traceable and intraceable problems here. Thank you.